So today we're going to be talking about special logarithms. We've talked about our logarithms in the past and how they are the inverses for our exponentials. But we actually have a couple of special logarithms that we need to go over because you see them a lot in your upper level mathematics as well as a lot of your science classes. So there are two special bases for our logarithms, and they are the bases of 10 and e. Okay, so our base of 10 is what we call our common logarithm. So we have log base 10 of x, okay? And that's going to equal just log of x. So because our 10 is a base that occurs a lot, basically mathematicians got lazy and were like, I'm tired of writing this 10 over and over and over again, so they just dropped it. So anytime that there's not a base on a logarithm, it's an understood 10. Now, for our natural base is this variable that's called e. And e is a lot like pi in the fact that it is an approximation. It is an irrational number. Again, remember our irrational numbers are going to be decimals that do not repeat and do not end. So our e is going to be approximately 2.7183. And it continues on, but that's it rounded to 4 decimals. Just like pi, it's going to go on forever. Now, for our natural log, basically what we're looking at is if I have log base e of x, again, because it happens so often, we end up just writing it as the natural log of x. Now, that is an L, not an I, so be careful with that. And we do read it the natural log instead of log natural. And the reason for that is because of the Greek word that actually means natural log. And if you look at your calculator, you're going to see both a log button and a natural log button. And we will be using those. And so you need to make sure that you're familiar with where they are on your calculator, wherever you might be, whatever calculator you might be using. Now let's go ahead and look at some examples. Now remember that just because we have different bases, it doesn't change any of the stuff that we've learned thus far with our logarithms. So we can still convert things from logarithmic to exponential form or exponential to logarithmic form. The only difference is now we're going to be using those special bases that we just saw on the previous page. So on this first one, it asks us to rewrite each exponential equation in logarithmic form. So if I rewrote this, remember the important thing is that the base of our exponent becomes the base of our logarithm. Remember that logarithms equal exponents, so this is going to equal x, and 8 is going to be on the inside of my logarithm. So we have log base e of 8 equals x. But because now we know of this natural log, we know that instead of writing log base e, we can go ahead and write the natural log of 8 equals x. So basically I'm just kind of using that shorthand notation of the natural log. And our second, or part B, is going to be very similar. Again, if I were to rewrite it, we would have log base e of x, this time, equals 5. Again, remember logarithms equal exponents. So because 5 is my exponent, it's going to be on the right-hand side of my equation. But again, we want to use our special notation and write the natural log of x equals 5. Now, just like when we looked at our other types of logarithms, we can also go the opposite directions. Sometimes, depending on the question, we might need to have it in exponential form. Sometimes we might need to have it in logarithmic form. So we need to be able to go between the two. So here we have the natural log of x is approximately 0.7741. So remember that I can't see it, but remember that it's understood that this is technically a base of e. And remember that my base of my logarithm is going to be my base of my exponent. And so remember that logarithms equal exponents, so that 0.7741 is going to be my exponent. And then because we had an approximate sign in our first logarithmic form, we're also going to have an approximate sign in our exponential form. And then basically our x moves over to the other side. So e to the 0.7741 is going to be approximately x. Over here on the other side, we're going to do the same thing. So remember, we have an understood base of e. And so this would become e to the x power this time equals 10. And we do need to make sure that we can go from both our exponential to logarithmic form and also logarithmic to exponential form, no matter what our bases are. Now, there are a couple of different places that logarithms and exponentials come up in the real world. One of those is going to be like sound waves, so in decimals. So this example is dealing with a rock concert. So it says the loudness L in decibels of a sound is L equals 10 log of I divided by M, where I is the intensity of the sound and M is the minimum intensity of sound detectable by the human ear. Residents living several miles from a concert venue, pre-COVID days when we could actually have concerts, can hear the music at an intensity of 66.6 decibels. How many times the minimum intensity of sound detectable by the human ear was this sound if M is defined to be 1? So what we're going to do first, and it's usually a pretty good idea, is just kind of to rewrite the information that they give us, or draw a picture if it's a picture-y type question. In this case, we're not dealing with like shapes or anything like that, so we don't really need to draw a picture. However, I'm going to go ahead and write out the information that they give us, which is that equation. So I have L equals 10 log of I divided by M. Now the important thing to point out here, and hopefully what we notice, is that I don't have a base on my logarithm. And remember that a log is an operator, okay? I'm taking the log of I divided by M. I'm not multiplying it, okay? I'm not, doing anything like that. I'm taking the log of those things. And we have to have a base in order to take the log of anything on the inside. And remember from a few pages ago that this is going to be our common log. So this is actually an understood base of 10. Okay, and then I'm just going to kind of start plugging in some information that they give us. Well, the biggest key here is that they tell us that the minimum intensity that a human ear can hear, we're going to define to be 1. Okay, well, what's nice about that is if I divide anything by 1, we just get itself. So the equation becomes L equals 10 times log of I. And then it says how many times the minimum intensity of sound detectable by the human ear was this sound. And they kind of define for us where I is the intensity of the sound. So I is what we're going to be solving for. But it is going to be a little bit tricky because notice that that I is inside of our logarithm, so we're going to have to use some of our logarithmic solving skills. Okay, but we still have an L, so we need to figure out where that goes. Okay, it says residents living several miles from a concert venue can hear the music at an intensity of 66.6 decibels. Now, I don't really like the way that they word this problem because they say can hear the music at an intensity. So that's a little bit confusing because we defined I to be intensity. But the key here is notice that they say 66.6 decibels, and they told us that the L is what's in decibels. So we know that the L is what's going to be 66.6, and so that's what we're going to plug in there. Again, solving for our intensity or our I. Now remember when we talked about our logarithmic equations, we talked about how in order to solve for our logarithms, we have two kind of properties that we can use. The first we said is sometimes we want to rewrite it in exponential form, and the second is our equality property. Well, because I don't have a log on both sides, I can't use my equality property, but we could rewrite this in exponential form. But remember that before we can rewrite things in exponential form, my logarithm has to be by itself. And right now I kind of have a 10 hanging out to the front of that. So we would need to divide both sides by 10. Well, if I divide both sides by 10, I end up with 6.66 equals log base I. Sorry, log base 10 of I. And then from there, now since my logarithm is by itself, we can rewrite this, okay, in exponential form. Again, the key here is going to be that even though we don't have a base, remember that it's an understood 10. And that's important because in order to be able to rewrite in exponential form, we have to have a base. So remember that logarithms equal exponents. So my 6.66 is going to be my exponent. And because my I is what's on the inside of my logarithm, it's what goes on the right-hand side. Well, now that's nice. Our I is already solved for. It gives us stuff that just has numbers in it. So we can go ahead and plug all of that into our calculator. And you are going to get kind of a big number. So it is going to be 4,070,881.896. And that's intensity. So we don't really need to put a unit because it's just how many times the intensity. And so because intensity doesn't have a unit there, my number doesn't have to have a unit. And so that would be my answer. All right, so another key property that we haven't gone over yet is called our power property. Now remember that because our logarithms equal exponents, what ends up happening is if the stuff on the inside of my logarithm happens to have a exponent, we can actually bring that exponent down to the front. And the way where we get this from is remember that when we raise a power to another power, we end up multiplying those powers. Here, remember that a logarithm equals an exponent. So my log base 2 of 6 is an exponent. And so similar to my power property for my exponent or for my exponentials where I can multiply those two things, we can take our exponent of 5 that's on the inside and multiply it by the exponent that we know log base 2 of 6 is going to turn into. And so this is going to be an important property, and we'll see why in just a second. So remember, up until now, when we've solved exponential equations, we've looked at things that we could rewrite with the same base. So we would have 4 to the x equals 16, and we can rewrite 16 as 4 squared. However, sometimes we're going to run into things where that's not the case, where we can't rewrite it using the same base. So like on our first example here, we have 4 to the x equals 19. There's not a way for me to rewrite 19 with a base of 4. And remember that because that x is in the exponent, we can't just divide by the 4 or get rid of the 4 or do anything with the 4 until we take care of that exponent. And that's where our logarithms are going to come into play. So what we're going to do is just like you would any of your other types of operations, where we want to multiply both sides by something or divide both sides by something. Here, what we're going to actually do is take the log of both sides. And we're going to go ahead and use our common log, okay, and take the common log of both sides. So that's going to become log of 4 to the x equals log of 19. And again, I'm using a common log because it's easy to calculate on our calculator. Because depending on what type of calculator you have, you can't always plug in different types of bases. But all of our calculators should have our common log, or remember, which is a base of 10. And here's where that power property is going to come in handy. So notice that I have log of 4 to the x. My x is acting as an exponent on the inside of our log. So we're allowed, just like our property said, to multiply that or pull it to the outside. And that's handy now because notice that we can now get rid of our log of 4. Okay, so before, when our x was still inside of our exponent or then inside of our logarithm, we couldn't do anything to undo it. But now, notice I have x times the log of 4, so we can undo the log of 4 by dividing both sides by log of 4. And so then we're just going to plug all of that into our calculator. There's going to be an important thing though, so you're going to type in log 19, and you need to make sure that you end that parentheses around your 19 before you click your division bar. And when you plug all of that in, you're going to get approximately, and they tell us to round to the nearest 10,000th, which remember is 4 decimal spots. So we get 2.1240. So let's do one more example like this. Again, I have a 3 to the x equals 15. If we think about it, again, there's not a way that we can rewrite 15 as a base of 3. Now, there's a way that we could rewrite with multiplication, but if I have an exponential equation, that's not going to cut it. It's not going to help us to do that. So this is going to be the same as our first example. We need to take the logarithm of both sides. So I would have log of 3 to the x equals log of 15. Again, then we want to use that power property to get our x out of the exponent. So we're going to multiply it to the front. And then we just have x times log of 3, which helps us because now we can divide both sides by a log of 3, which allows us to get x by itself. So we get that x equals log of 15 divided by log of 3. Now, if I asked you for the exact answer, that would be your final answer, because from there, the only thing that we can do is plug that into our calculator and get a decimal approximation. Now, if it says to approximate or round to the nearest whatever, then you're going to go ahead and plug it into your calculator. And here we get 2.4650. So please make sure that you know how to plug in your logarithms and those operators into your calculator, because that's going to be important for your test when you're having to solve these exponential equations. All right, let's look at one last example. So notice here I have a base of e. So it's going to be a little bit different, but not entirely. So we have 4 times e to the negative 2x minus 5 equals 3. So remember, just like with any of our other things, before we can start moving things around or taking logarithms or anything like that, whatever's being raised to the exponent has to be by itself, which means that right now we have to get rid of this 5 first. So we would add 5 to both sides. Then we would want to divide both sides by 4. So we get e to the negative 2x equals 2. Now, from here, it's a little bit different because notice we have a base of e already. So if we have a base of e, usually that's going to be a good indicator that we can go ahead and try and rewrite it in logarithmic form and see if that gets the exponent away. Okay? Now with our other ones, we had like different types of bases, like 4s and 5s and whatnot. So that's when we took the log of both sides. Here, I'm going to try and just rewrite it in logarithmic form. So we have e to the 2x equals 2. So remember that my base of my exponent becomes my base of my log. But also recall that if I have a base of e, that becomes the natural log. So we would have a base of e, but remember that becomes the natural log. Remember that logarithms equal our exponent, so they're going to equal negative 2x. And then 2 is what's going to be in the inside of my logarithm. And then my last step is going to be to divide by that negative 2. So we get that x equals the natural log of 2 divided by negative 2. From there, we would need to plug that into our calculator using our natural log button this time. But again, making sure that you end your parenthesis after your 2 inside of the natural log. And again, it tells us to round to the nearest 10,000th, so we should get negative 0.3466. So make sure that we can use that natural log button and that we're getting the correct answer. Now we have one last one to look at for our equations. And this time, notice that this time we have a natural log. We have a logarithmic equation instead of an exponential. Again, we've looked at solving logarithmics. The only difference here is that this time we have a natural log instead of a log with a different base. But it's still going to work very similarly. Remember that my first goal always, before we can start doing anything else, is that my logarithm has to be by itself. So in this case, we have a 3 hanging out on the outside, so we would need to divide both sides by 3. So we have 24 divided by 3 gives us 8. Now please be careful, because remember our natural log and all of our logarithms are operators. So I am taking the natural log of force x. So just like if I had the square root of 4x, I can't get rid of the 4 without taking the square root of it. Here, I can't get rid of the 4 without getting rid of or taking care of that natural log first. So please don't try and divide by 4, because again, it's inside of my natural log. So we need to undo that first. And we're going to undo that by rewriting it in exponential form. So remember that my base of my logarithm becomes my base of my exponent. And in this case, we don't see a base, but remember that our natural log has an understood base of e. And remember, logarithms equal exponents, so 8 becomes my exponent, and 4x goes onto the other side. So then in order to solve, we would divide both sides by 4, and we get that x equals e to the 8th divided by 4. If I asked you for the exact answer, that would be your final answer. But in this case, it asks us to round to the nearest 10,000th. There is an E button on your calculator, whether you have the scientific calculator or your graphing calculator. So you're going to type in that E button, raise it to the 8th power, and then divide by 4. So you should get 745.2395. So make sure that we've all found that E button on our calculator, because it's going to be really helpful. And then for most of us, the power button is going to be what's called the caret button, or it kind of looks like the top of a triangle, so without the base. All right, and the last thing that we're going to think about or look at is called our change of base formula. Now, looking at some of these problems, we noticed that our calculator has a log button, which remember is our common log, and we also have a natural log button, which is the base of e. Now, some of your newer calculators, like your graphing calculators, actually have a way for you to be able to type in different logs, but that hasn't always been the case. And then actually even before that, which I know it's hard to think about, before there were calculators, okay, you couldn't plug that in. And so what we had were these tables that were called log tables that were in the front or back of your textbook. And what they did were they gave you these different approximations of different types of logarithms. That way you could then use those decimals. But the problem was, is in order to put like lots of numbers in there, it was much easier just to stick with one base instead of having to do like an infinite number of bases. So what they decided was, okay, we have this change of base formula, which is what you see. So basically what it allows us to do is to change a base into any other type of base. And so they chose the base of 10. And so basically they converted all of their other logarithms to bases of 10. That way then on that table, you only had to have bases of 10. And then for us, more currently, if you have a scientific calculator, it's not going to have a button that allows you to change your base. So be careful, because remember that like in our example here that we see, we have a base of 3, okay? So that doesn't mean that I'm dividing the 20 by a 3. It means that I'm taking the logarithm with a base of 3. So if your calculator doesn't have a base button for your logarithm, we can use this formula then to allow us to be able to plug it into our calculator. So if we have log base 3, notice that my 3 is in the place of my a for my formula, and my 20 is in the base, or is in the place of my n for my formula. And it specifically tells us that we want common logarithms, which means that we're going to make our b value equal 10, kind of like they did in our example. So log base 3 of 20 is going to become log base 10, but remember, if I have a base 10, I don't have to write it, so it's going to be of 20. I'm going to draw my division bar, and then I have log of 3. And now, all of us should have a calculator that allows us to type in our logarithms. So now we can type in log of 20 divided by log of 3. And it's going to be important, again, that we end that parentheses around our 20. So using our calculator, plugging that all in, we should get that log base 3 of 20 is approximately 2.7268. And so now this will allow us to evaluate any type of logarithm that we need to evaluate. And then also, I could also ask you, just convert this logarithm to common bases. And that would be another way that I could ask you something like that on your test. So remember, the key thing from this lesson is that really, even with our bases of 10s or our bases of e's, they still act like all of our other logarithms. So all of the other things that we've been doing still apply. You just have to remember that your common logarithm has a base of 10, and your natural logarithm has a base of e.